In chapter 20, the last chapter of the semester, we will be looking at synthetic polymers and biopolymers. So in this presentation, we'll concentrate mostly on synthetic polymers. So we'll give the importance of polymers in today's society, and we'll define polymers. What is the definition in terms of chemical definition? Then we'll look at the different ways polymerization can occur. What you'll discover is that they occur basically through most of the reactions that we've covered, the reaction type that we have covered. So the first type we'll look at is cationic polymerization. Then we'll look at anionic polymerization, and then radical polymerization. As you can imagine, these are intermediates. The cation is a positive charged intermediate. The anion is a negatively charged intermediate. And the radical is intermediate, which has a lone pair of electrons. Lastly, we look at copolymerization, and we will conclude with some examples of polymerization. So let's begin. Polymers are everywhere, as shown here. I am sure we have heard of polymers in our everyday life. Here's some examples. Water bottles, the containers that we use in our everyday life, saran wrap, rubber, topware, face shield, plastic bags. They are all polymers. And of course, what we'll do in this lecture is we'll study the process of polymerization. So first, let's get into the definition. Polymerization here is a chemical process in which simple units known as monomers are transformed into polymers. Remember here, poly means many, and monomer here means one. So it's basically taking a monomer, many monomers, shown by N here, through the process of polymerization, which we'll be discussing, to give us a polymer where the X's or the monomers are all joined here by chemical bonds. And of course, to create a chemical bond, as you know, there has to be a reaction. There are different types of polymers, however. If we have polymers with one unit, we say it's the simple polymer. But if we have polymer with more than one monomers, there are different possibilities. And shown here are first the alternating polymers. So we have A, B, and it alternates. So we have two types of monomers here, A and B. The next type is a block polymer, where all the A's form a block, that monomer, and all the B's form another block, etc., etc. And of course, as you can imagine, the last possibility is the random. There's no set systematic way of the bonding here. They just randomly bond together. The monomers just randomly bond together. Let us look here at the properties and some of the polymers that we are familiar with. Here's one polymer, polyethylene, that's used to make plastic bottles. As we know, very flexible, we can squeeze the plastic bottles, etc. The monomer that's used to make that is CH2, ethylene. Here's another one, and this is the vinyl chloride molecule. vinyl, because this carbon here is the vinylic carbon, and of course we have a chlorine, so it's vinyl chloride, and the polymer is polyvinyl chloride, or PVC. So we are familiar with PVC piping. We know that's very rigid, and it's used in plumbing pipes and tubes. A couple more. Here's another one, polystyrene. So this is the styrene molecule as the monomer. Through the process of polymerization, we get polystyrene, and this is also used in packing material. Here's one that was a few years ago. It was very popular, and this is the CF2. And when it's polymerized, the product is called Teflon. Of course, as you have seen, it's used on cooking surfaces because it's highly resistant to sticking, and of course it's pretty stable at high temperatures. So that's why it's very, very useful. And we have some others here that you can read up on. So here's an example of making a polymer. So here's a polymer. So let's see how we can make that. So if we have here an alkene in the presence of an acid, remember an acid here is a proton donor. So here is a proton, H plus, H without its electrons. Here's a double bond, a nucleophile or Lewis base. It will react with the proton to give a carbocation. No surprise there. We have been doing that all semester. But once a carbocation is created, it is now an electrophile. So in the presence of another molecule that has a double bond, which is nucleophilic, you can see that a bond is made right here, and we have created another carbocation. So this process keeps going and going and going. So we represent here N to show the number of units that are bonded together. Of course, this is an intermediate, so in a termination step, we can form a double bond right here, as shown by losing a proton. So if we took a proton here, throw in the electrons here, we have a double bond, and this is now a neutral molecule, and that's a polymer, where N here represents the number of units or monomers that's incorporated. They're typically in the hundreds. Let us look at another example of a cationic polymerization. Cationic means that the intermediate is a cation. So here's styrene. In the presence of an acid, we protonate. It's protonated. These electrons bond to the proton to form here, in this case, a benzylic carbocation. Very stable due to the resonance of the benzene ring. But in the presence of another styrene molecule, these electrons can bond to that carbon, and we have another very stable carbocation here. And of course, as you can see, the process goes on and it continues, and in a termination step, losing a proton, we have here the polymer, where N here represents the number of units, or the number of monomers, or the number of styrene units to form the polymer, or the polystyrene in this case. Let us look at a different type of intermediate, the anionic. That's the negative. That's the anion. So here's an example of a monomer, 1,1-dicyanoethane. So here's this cyano group here, two cyano groups bonded to this carbon. And in the presence of a trace amount of OH, it bonds here. And of course, we have a very stable resonance structure, putting the negative charge here and two electrons. That's stable because that negative charge and the two electrons can be delocalized into any of these cyano groups. Pretty stable. So in the presence of another reactant or monomer, a reaction will occur here to create another anion. As you can imagine, the process continues until we get here, and in the presence of an acid, just a trace amount of acid, we can protonate this, and we have here a termination, and this is our polymer. So that's how the anionic polymerization works, because the intermediate is an anion. Let's look at the third type, radical. So, if a radical is generated, of course we have seen that before. We have a bond here that's pretty weak, and of course it's bonded to the same atom, so the electrons are equally distributed here. So if energy is supplied, one electron goes over here and one electron goes over here to form a radical. So that's a radical. You know from your reactions before, a radical is an intermediate, not stable. So in the presence of isobutene, for example, it will form a bond right here, and of course a radical, a tertiary radical will be generated. So as you can imagine, in the presence of another monomer, it continues to react, forming another stable radical. And if we have more, such as N, there is a long chain which we have N number of units involved. And of course, in a termination step, we have the radical bond in here and here to form this bond right here, and that's our polymer. So again, you've seen these steps before. This step is called the initiation step. This step is called the propagation step because more radicals are propagating here. And the final step is called the termination step because it couples radicals or terminates the radicals that are in the vessel. Here are two radical initiators. We call them radical initiators because we have a weak bond here. Benzoyl peroxide, in the presence of heat, this bond here, because it's bonded to two oxygens, it's a covalent bond, and these electrons are equally distributed. So when it breaks, there is a heterolytic cleavage of this bond here, putting one electron on the oxygen, and we have two radicals. As you can see here, it's pretty stable because we can draw a resonance structure, putting this radical onto this oxygen over here. So this is the radical initiator that now reacts with the monomers to form the polymers. Here's another one, AIBN, azobisbutyryl nitrile. As you can see here, in the presence of heat, just a small amount of heat, this bond here breaks. Put electron here, put electron here. You recognize that to be nitrogen, and another electron goes right over here, and another one goes here to form two of these radicals. Again, that's pretty stable because this electron here can delocalize into the cyano group. I'll just give you one example. So one electron here, and another one on the nitrogen. So there's a delocalization. So this is your radical initiator. So this reacts with monomers to form polymers in the end. Let us turn our attention now to copolymers. Here's where we have more than one type of intermediates. As I mentioned earlier, there's the alternating, and there's the block, and there's the random. And these type arrangements are dictated by the reaction conditions. So in industry, by using different concentrations and different reaction conditions, they can get different types of polymers here. So let us look here at copolymerization between two molecules. This time we're using the cationic polymerization. So here's isobutene, double bond, which is a Lewis base, and here we have H plus, an acid, just to start the reaction. So we can have a bond here to generate here the cation. So if at this point we introduce styrene, which has a double bond here, notice this is the double bond that's reactive, not in the benzene ring. Why? Because as we know, these electrons in the benzene ring form part of the conjugation, which makes it aromatic. So those electrons are not very reactive. Remember, whenever they are reacting, we have to use a catalyst. But in this case, these electrons here of this double bond for styrene, those are the electrons that are reactive. So these electrons react with this carbocation to generate another carbocation here, and this is called the benzylic carbocation. It reacts with another molecule of the isobutene, and of course, as you can imagine, generates another carbocation, pardon me, and it keeps going until we have our polymer here, copolymer, which is made from styrene and isobutene. As you can imagine, what's done in industry, they have available to them a wide range of different monomers. And by making different mixtures, they can get polymers of different quality and different properties. And that's why we have so many different types of polymers on the market today. Here's another type of copolymerization. This one is Bisphenol A. By the way, you're very familiar with Bisphenol A. I think you had that as one of the questions on the last exam. But notice here that if you mix Bisphenol A with this molecule, let's analyze this molecule carefully. It's a difunctional molecule which has an epoxide here and a good leaving group. So in a base, as you can imagine, this is the acidic hydrogen. So it will take off this hydrogen or abstract this hydrogen to form a conjugate base. It will react here. By the way, the mechanism is on the next page. Next slide. It will react here and keep going until we have an epoxy resin here. So here's a polymer. N here, of course, represents a number of repeating units here. And because this is a copolymer, the repeating unit is not just one type monomer, but two, coming from these two reactants. Of course, as you know, epoxy resin are used a lot in industry today. We'll have more examples at the end. But let's look at the mechanism for that reaction. So as I mentioned, in the presence of a base, it will abstract the hydrogen or the proton to form this. The nucleophile, so here's a nucleophile now with 2 electrons here. This nucleophile attacks this epoxide or this oxyrane. Don't forget the chemistry we have done. In a basic medium, the oxyrane will be attacked at the least hindered carbon. Here's the least hindered carbon. This one is more crowded. So it attacks here and it opens up. We have a leaving group left here. So we have a nucleophile and a leaving group, so we can form another epoxide again. You know what's happening on the next slide. It just keeps going. It just keeps going. So on the next slide here, we can have another mole of the one of the monomers attack here and keeps going until we have the resin, as we showed on the previous couple slides. So this is an example of a copolymer the polymerization of two different monomers to form a very important type of polymer called a resin. And of course, as you can see here, it's highly viscous and mainly used as adhesive and coatings for different surfaces. So again, polymers are very important in industry. Very important in industry and of course in everyday life, because we find it very useful in just about everything that we purchase. Let's look at some practical examples here. These are different type reactions, but it's a copolymerization. Let's look at this molecule here. It's an ester. It has an ester functional group here. And the other molecule, a monomer here, is ethylene glycol. It has an OH, actually has two OHs here. But let's concentrate on this OH for the time being, and this ester for the time being. You know from your chemistry, if you should heat this up, supply some energy, there'll be an acyl substitution. In other words, a transesterification where this group here comes in and this comes off as methanol, and we have a new bond over here, a new ester. As you can imagine, here is another OH, and here is another ester back here, so this can keep going until we have here the polymer that's shown here. Notice again, it's a copolymer, so this is coming from this molecule here, this monomer, and this portion here is coming from this monomer, e.g. This type polymer that's made from this ester bond here is widely used in society, used as fibers. You've probably heard about polyesters, yarns and ropes, very strong ropes. Go to the hardware store, you'll see most of the ropes that are made from polyester, which is a polymer shown here. Safety belts, that type of stuff. So this again is a transesterification using two monomers here. Let's look at another example. Here is another type chemistry we have done before. This is a carboxylic acid here. So let's concentrate on this carboxylic acid functionality. And this other molecule here has an amine functionality. So let's concentrate on that. If we should heat this up, what should happen is we have a substitution, an acyl substitution, where this comes off as water, as shown here, and this nitrogen now bonds to that carbon, and here we have that bond right here. So we've made here an amide bond. So it's a polyamide. As you can imagine, here's another amine, and here is another acid, carboxylic acid. So this reaction will continue, as shown here, N number of copolymerization to form this polymer known as Kevlar. And as you can see here, Kevlar is an extremely strong, lightweight polymer that's resistant to heat and corrosion. So it has many practical functions. By the way, Kevlar is, I think, the trademark name for that type compound. What industries do is that they patent these processes and patent the actual name of it so that they can actually market it under their name. And let's look at another one here. So you can see here we have a carboxylic acid again. Notice a diacid, and another one here which is a diamine. So we have an amine reacting with an acid in the presence of heat, Same type reaction as we've seen before. Water comes off, as shown here, and this nitrogen bonds to that carbonyl carbon, and we have that bond right here. And it's an amide bond. Again, we have another amine back here, amide bond, right? So we have an amine functionality here, an amine, and a carboxylic acid functionality here. So as you can imagine, it can continue with a copolymerization, where the main bond here is the amide bond. This type polymer is known as nylon 66, or nylon, and it was one of the first polymers, that synthetic polymers made, and used a lot in clothing. I think stockings and that type clothing. That's the nylon fabric. And lastly, let's look at this one. Here's bisphenol A again. As you can see, that these compounds are very important compounds in industry. Now we have the basic salts. It's just a matter of adding this compound in a basic medium. So here we have a nucleophile. Let's look at this compound here, phosgene. Very, very, very toxic substance, but under controlled reaction conditions, it's very, very useful. So phosgene is here, but let's analyze it. Good leaving group, good leaving group. Carbonyl carbon, which is partially positive because it's bonded to a negative oxygen, and very electronegative chlorine. So as you can imagine, very, very reactive. So this would come in and kick out a chlorine. It still has another chlorine left, however. So you have another molecule coming in and bonded here to kick out this other chlorine here. So we have what's called here a carbonate bond, because we have two good leaving groups bonded to one of the monomers, in this case phosgene. This is a polycarbonate and Lexan, and this is a very sturdy compound, and it's used for windows and windshields and reusable drinking bottles, the hard types, DVDs and CDs. So as you can see, the properties of these polymers, they vary depending on the monomers that's used here. By the way, there's a spelling here, I'll fix that. So I think this is the end of the presentation here for the synthetic polymers. So I hope you can see that organic chemistry here is getting a little easier, because now we're just applying all the chemistry and reactions that we've learned to build or to synthesize practical molecules, in this case polymers. So once again, remember that we're scientists here. So in addition to learning the content and these reactions and the facts, our job is also to be able to apply them to solving problems. If you go to work in industry, your job will be to take your knowledge of polymerization and see if you can make some new polymers that will be of use to society. So continue to study hard and make sure that you, in addition to understanding the material, you are using the training learned here in organic chemistry to be good problem solvers. So I'll post more information on D2L, so look out for that. Okay?